All right, Nikhita, you ready?
Yeah, thank you for the
All right,
invitation.
go ahead and take it away. Thanks so much.
All right. A little bit more about FreeClimb before we get into the presentation. So FreeClimb from Whale helps companies build exceptional customer experiences. We have the industry's most intelligent and scalable communications platform, and we're going to show you what the platform is capable of today. Today's topic includes a bit of background about domain-specific speech recognition and how these models compare to general ASR models. We will also talk about how ASRs work and then go into bespoke model training lifecycle as well as considerations before and after you train your models. So these days, LLM chatbots and LLM voice-based chatbots are very common. But when you apply these kind of chatbots to customer service, there are a bunch of concerns which show up. For example, there might be privacy concerns as you might share user conversations when you use third-party APIs. These LLMs also have limited context and they struggle with longer conversations. There's also issues with dependability. They can hallucinate, they can go off topic, there can be inconsistency in performance, so it's hard to control these large language models. Apart from that, there's also high usage costs, so you might be paying for just licensing the model, using it, and then as you use it more at scale, it can get pretty expensive. There's also other challenges. These require a lot of resources and they might not be everyone's cup of tea. But there is another way to go about these chatbots for customer service. And in our experience, using a speech recognition model in combination with an NLU model based on your use case, for example, for intent recognition or summarization, the combination of these two models separately is a more robust solution. There are two ways of going about this. So if you want high ASR transcript accuracy, you can either use domain general models or you could use domain-specific small vocabulary models. You need to have good transcription because once you have good ASR transcripts, you can do a lot more with those transcripts. So if the ASR gives you accurate results, you can improve your downstream capabilities as well. Without accurate transcripts, it's hard to do anything else with that text. So if you go the domain general model route, there are a bunch of options available. For example, Speechmatics, there's Google Speech-to-Text, there's Whisper. But the problem with these models is that they are unable to recognize domain-specific words. So if you have a specialized domain, there might be certain words like, for example, in home automation, if you have a customer service chatbot for home automation, you might want it to recognize product names that you use in the house and other things like that. So these models can recognize them, but not with very high accuracy. And we'll show you some examples in the further slides. On top of that, there is also latency issues. Some of these are slower and might not work if you want to use it in an online or real-time format. So that's also something to consider. There's also, again, these are the highly accurate versions of these models, or the newer versions might not be free, so you might have to pay for these models. And there's also high resource utilization, again, as was with the LLMs. So there are all these disadvantages of using domain general models. But if you move to custom domain-specific models, first of all, these are very flexible and customizable. You can train them to recognize the specific words you want. They are also adaptable to channel-specific noise. So a lot of large language models are trained on clean-sounding audio, and they might suffer and have bad error rates for noisy channels. So depending on your domain, you can adapt these domain-specific models accordingly. And they also require less resources. And again, because these are in-house, they are faster, they don't cost that much. So here we show an example of one of the domain general models, Whisper. And we applied this on our specific customer survey domain. And this is just a chatbot that we have in-house, and we trained our own model using Caldi. So Caldi is a open source toolkit that we use to train our ASR models. So we provided it our data and tuned it for this specific domain. So as you can see in the first column, not only is this model requiring much less audio, 75 hours versus the, I don't know how many thousands of hours of audio for Whisper. These also take less time to train and are smaller in size, so you can load them and they require less resources in general. Not only are the open source or not the large language models, not only are they more big and harder to train, they also don't have the most accurate results. So as you can see here, on our domain, on our subset, this has a word error rate of 17 to 20%. And you can compare it to the word error rate of 9% that we see with our bespoke model. So that's a huge, it's almost half of the word error rate. And I'll describe word error rate more later. But essentially, the lower the number, the better. So the less mistakes your speech recognition engine makes. If you look at latency on an NVIDIA A100 GPU, if you use the base Whisper model, for a 125-second audio, it takes about 4 seconds to decode. So you can see that you might have, if you use Whisper, you might have this lag where the user is still waiting for the response because the transcription is taking a long time. But if you use the bespoke models for the same audio, we get the result in milliseconds. So that's just a fraction of the time it takes while using Whisper. And if you want more accurate results, and if you decide to use larger models, they are even more slow compared to the base model. So you can see how you can have an advantage if you use domain-specific models. There is a question of why this word error rate is high and why speech recognition is hard in general. And there is a bunch of reasons for that. It's a difficult problem to solve because a lot of the times the audio can be recorded in different ways. It can be conversational speech, it can be read speech. There's also variation in the speakers, so accents, speed of talking, age of the speaker, all of that affects speech recognition and causes variability. Again, there's also background noise and the impact of that on speech recognition. So if you train on mostly quiet environment data, you will struggle with noisy environment decoding. So let's dive into how ASRs work. After that, we'll dive into the bespoke model training. So in general, a traditional ASR system has the following components: a lexicon, which is a dictionary, an acoustic model, and a language model. And in combination, these form a decoding graph. And so once you have your input audio, you can get the most likely words spoken if you use this decoding graph. So the data that you require to train such a speech recognition model comprises of the audio data and the corresponding human transcripts. So if you have sufficient data, you can train your own speech recognition model. So if you think about it, you have audio data and you need to somehow map it to the words being spoken. So the first step would be to digitalize this and somehow convert the sound into some sort of features that you can train on. So this can be done using, like if there's human speech, you can obviously record it through a microphone that generates a spectrogram that represents, as you can see here, with time, there's frequency and intensity that's mapped. So this generates a spectrogram, and then you can use these different features to represent that audio. And the idea here is that we want to capture what is being said, and we want to discard any unnecessary noise. So you can use MFCC features and CMVN features. These are very commonly used in speech recognition. So these represent the content of each utterance. And then I vectors are different type of features which can be used to represent the style of the audio or focus more on the speaker characteristics. So with these three features, you can digitalize your audio and start training. You might think how we will, for longer audio, how does this work? So typically there's a sliding window of 25 milliseconds and 10 milliseconds apart, and then you generate features for each of these slices of audio. And these are called acoustic frames. So essentially, the goal here is to predict the most likely words spoken given a set of features. So you can write this as probability of the word being spoken given certain features X. If you apply Bayes' theorem to this, this can be written as probability of the features given the word and the probability of the words. So the first part forms the acoustic model, and the second half forms the language model. And we look at more details about what these different parts are. So the acoustic model deals with the raw audio waveforms, and what it's trying to do is predict what phoneme, or we'll dive into phonemes later, but what word is being spoken in each audio frame. And for the language model, it tries to guide the acoustic model, and it discards predictions which are improbable. So given the text transcripts that you have, you can train a language model, and it will help you frame grammatically correct sentences and discard words which sound similar but don't belong to your domain. So that's where the speech recognition models get their edge from. So in speech recognition, we do not train directly to recognize words. Instead of that, we try to recognize phonemes for each audio frame. The reason being that if you look at the vocabulary, in English vocabulary, there can be a lot of words, and that will be too many classes. So we work with phonemes instead. And this phonetic data and phonetic representation of words is usually easily available. These are curated by industry experts and language experts who give this representation for each word. So for example, American English has about 44 phonemes, and a phoneme is basically a distinct unit of sound that distinguishes one word from another. So this, for English, you can download this as the CMU dictionary. It's readily available, and it looks something like this. So for each word, you have the phonetic representation available already. And this is called the lexicon, and this is one of the parts of the ASR system. And inside, if you have a closer look, this is represented using Markov chains and HMM modeling, and it can also account for handling variation in timing. So if somebody was to say 6, they could say 6, or they could say 6. Like, you can emphasize on different parts of the word, and the HMM can handle that variability by the self-looping. So once you have that breakdown, essentially, we talked about features, we talked about phonemes. So now we need to understand the mapping between them. And that is done using either HMM, GMM models, or more recently, using neural networks. So the main idea is that the acoustic model is going to learn the relationship between a given sequence of features and map it to a given sequence of phonemes. So because we have audio and the corresponding text, we can learn this over a lot of hours of data and learn what phoneme sounds. We can learn the relationship between the features and the phonemes in that way. So like I mentioned, you can do this through GMM, HMM modeling, or you could even do this through neural networks. There are different architectures for the acoustic model. Even in the hybrid neural network systems, you could have different layers. You can play around with a lot of parameters there to optimize it for your particular domain. So once you have the acoustic model, you've learned the relationship between the acoustic features and the phonemes. And now you have to make sense of the phonemes and generate sentences. So that's where the language model comes in. So the language model calculates the likelihood of a sequence of words. So if you give it one word, it predicts the probability, it predicts the next word given the previous word. And this is where the vocabulary plays a role. So depending on what words are very common, in your data set, it can better predict the word that is being said. So if there are similar sounding words, the language model helps to choose between which word should be selected as the output. So for example, if somebody said recognize speech, it could also be mistaken as recognize speech. So that distinction is made in the language model. And language models are typically n-gram-based models. So if you have a bigram model and if you wanted to find the probability of this sentence, it can be written as the probability of the first word, and then you can have this conditional probability. So since it's a bigram model, it will only depend on the previous word. So probability of simplicity, then probability of the second word given the first word, and so on. So this is how the language model makes predictions. So putting all of these together, this process is called the decoding process. And so we have the input audio, we extract the features, we get the phoneme from the acoustic model, and then we use the language model to build out the sentences. So once you have a system, you want to ensure that it is performing well, and you need to evaluate it in some way. So the common metric used for evaluation is the word error rate. And the word error rate compares the predicted output to the reference or the human transcript. So once you have both of these, you can compare them word by word. And wherever there are errors, you can categorize them as insertion, deletion, or substitutions. And this is based on Levenshtein distance. And the idea is that how many number of edits are required to change the hypothesis to the reference transcript. That's what the word error rate is trying to calculate. So for example, if you have a human transcript as the dog is under the table, and your model gives a predicted output of the dog is dash the fable. So you can see that there's one deletion here and one substitution. So that's how the word error rate is calculated. And we want this number to be smaller because the smaller the word error rate, the higher the accuracy. And you can see that there might be some issues with the way the word error rate is being calculated. It does have some disadvantages. So the word error rate calculation cannot differentiate between certain words, if certain words are more important than the others. So if there are keywords in the transcript and your model misses them out, that might just be equal to like missing out a filler word like to or the. So the word error rate metric cannot capture those kind of differences. And it also doesn't have any idea about how wrong a word is. For example, if you look at the reference here, I want to pay my bill versus I want to say my bill, it's not that bad. It doesn't look that bad. And you can kind of make out what is being said. But the word error rate would still be the same if you say missed out on pay entirely. So it doesn't have an idea of how off your, how bad your transcript is. It just looks at the words one at a time. So with that, let's move to the next section, which is considerations for training your bespoke model. So this is what the training life cycle looks like. So you have to define the scope, gather data to pre-processing, train your model, and then evaluate it. If it meets your expectations, you can deploy it and then keep on updating it as necessary. So we're going to dive into each of those steps now. So first of all, you need to define the requirements and the scope. So depending on your domain, you have to figure out what is the vocabulary you're going to work with, what are the statements or the phrases that are essential for the model to recognize. Are there certain words which are more important that should definitely be recognized, and so on. So it's best to scope this out before you start training so that you can get a better understanding of your model. Here are some examples, like for home automation, like I mentioned earlier, there might be product names that are essential to be recognized. So like turn on the Dyson vacuum cleaner in an hour. So if your model does not recognize Dyson in this case, that might be a problem. Somebody might have multiple vacuum cleaners. They want to turn on a specific one. So it's important to get these keywords right. And if it's a different domain, like for a financial chatbot, you might have some phrase like, what is the balance on my credit card ending in so and so. So for a financial chatbot, recognizing numbers correctly might be more important. So you have to figure out, based on your domain, what the vocabulary would look like. So once you have that, there are some requirements for the training data itself. You might be wondering, how much data do we need? So typically for limited vocabulary models, in our experience, you need at least 25 hours of data to see good results. And then you need high quality data as well. And by high quality, I mean that it should be reflective of how the application will be used, and it should be reflective of what how the users would interact with the system in production. It should also have sufficient gender and accent diversity, because if you don't have that, if you train, for example, if you just train on male data, your model will not do well for female speakers. So that, and similarly for accents, if you just train on, say, American English, and then if somebody has an Indian accent, the model might not do so well. There are other things to consider. For example, there are issues with data permission. You need to figure out how long you can keep the data. If there's PII, can you still use it? And do you need to do some kind of pre-processing before you start training? And it's important to note that we should ensure that most of the words in the vocabulary are well represented in training, because if that does not happen, the model will not do a good job in recognizing certain words. So that should also be ensured before a training is started. Next, you should also think about setting some performance expectations. So because you should have something to compare your model against, you should discuss things like, what is the expected word error rate, and how should it even be how should the model even be evaluated? Like I mentioned, word error rate does have some caveats. So should you use a custom weighted word error rate formula where you pay more emphasis on keywords and so on? So you have to figure out an evaluation strategy. And another thing to think about is what is like the acceptable latency. How much delay is okay in your application? Like we saw with Whisper, you can have up to 4 seconds delay. So if you have a real-time chatbot, this is not acceptable. So you should also think about how much traffic would be coming into the application and all these scalability issues as you start to train. Other than that, you should also figure out, how would you monitor the model? How often will you monitor the model? How often will you do updates? How will you do the updates? And one key point is that the users might not use your system in the same way as you thought initially. So there might be drift in how the people are talking to your system. And you need to have some kind of monitoring to figure out if there is any change. So once you have your data, once you have your high quality data set, there are a few pre-processing steps which might be necessary. For example, if you are dealing with very short utterances, you might have to do some padding of silences in the beginning and end, because there is a minimum length requirement when training with Caldi. That might change depending on what toolkit you use, but for Caldi, we do have to pad silences sometimes. You should also ensure that the text transcripts that you have are consistent. And this is especially important if you are dealing with different languages, especially the ones that have like accent marks. For example, you can have telephono represented in different ways. So you should ensure that throughout all your training data, you have consistent representation. Otherwise, this can lead to, two separate words and cause confusion in the model. There are other requirements for training, which is that you need GPU access. And for Caldi training, you do need exclusive access. And CPU-based training is very slow, so we do not recommend that. And and I did mention about monitoring the model. So you can regularly pull data from production and verify the performance. And this can, again, help in identifying if there's any drift, if there are unexpected ways users are talking to the system. For example, before COVID, nobody was really using the word COVID with a customer service application. And then all of a sudden, people started saying things like, I couldn't make my payment because of COVID. So if this was trained before COVID, the model would not be able to recognize this word, and you would not expect people to say this. But once you have regular A/B tests, you can identify these kind of issues and rectify the situation. There's also, so the first time that you test your model, you can obviously have a subset set aside for testing and ensure that you are seeing decent performance before you deploy the model. Some more interesting things that we found while training these kind of models is that sometimes it's necessary to retrain the model and update it, especially if you're adding some new functionality or if you're trying to accommodate some mistakes that you saw during A/B tests. So this requires specific utterances for the targeted word or phrase which the model is getting incorrectly. So again, you should ensure that you have enough gender and accent diversity for these utterances. And typically, in our experience, about 200 utterances for a new phrase generally suffice, and the model is able to recognize that word once you retrain it. We also trained different models. So apart from English models, we trained Spanish models as well. And we did notice something interesting, that even though people say that they want to talk in Spanish, sometimes they can alternate between multiple languages. So for example, for a user, they might say something like add hotspot in Spanish. And if you have a custom model, you can add these English words in the model as well. But if you have a generic ASR, most of the times they failed in recognizing these English words. So this again shows how customizable these models are. So you can imagine that this can be expanded to more specific vocabulary. If you have a lab environment where you have a chatbot, there might be certain instrument names which are in English, which you might want to incorporate. So as long as you have sufficient training data, you can accommodate these in the custom models. Here we show some of the results from the models that we trained. So this is for a specific domain. We have both English and Spanish models. And you can see here there is a domain-specific model as well as a commercial ASR engine. So for our English model, we saw word error rate as low as 5%, whereas with the commercial ASR engine, for this particular domain, the word error rate was 33%. So you can see that is a huge difference. And if you can reduce errors at this ASR transcript level, you can do very well in the downstream NLP tasks. Similarly, for Spanish, we have a model, custom model, which got the word error rate down from 24 to 14%. And if you look at the keyword specific error rate, you can see a huge difference here. And you can imagine how important this would be in doing tasks like intent recognition or summarization once you have the correct transcript. So to summarize, domain-specific ASRs can reach high accuracy levels for specialized vocabularies, and these can even outperform state-of-the-art domain general models. We talked about how customizable these models are and how they can be adapted to specific languages, and they are also adaptable to different channel constraints. So you don't have to worry about the user being in a noisy environment and so on, because the model can be trained for those kind of things. These models are hosted in-house, and they aren't susceptible to security or privacy concerns because all of the data is kept in-house. You're not accessing any third-party API, so you don't have to worry about those kind of things. And these are also cheaper than using paid ASR solutions. So we can help you guys build your own custom domain-specific models. With that, I would like to open it up for questions.
Well, thank you so much, Nikhita. That was a fantastic presentation. And there have been some questions that have come in. Mark Tucker asked the question, can your domain-specific models run on CPU and or let me see what he finished it with, either CPU and or GPU.
Yes, that's correct. So we can run these models on CPUs as well as GPUs. I did show the latency. So the latency numbers can differ based on where you run it. So you can run it on CPUs as well as GPUs. It depends on what your specific task is.
Great. Thank you so much. And I encourage anyone to please, this is a great time to submit any questions you have while we've got an audience here with Nikhita. Ken asks, is the bigram decoding model the most common versus trigram, excuse me, or a larger model?
No, so that was just an example to show you how things work. Typically, you at least need a 5 to 6 gram model to do well. But yeah, bigram model would be just too simple for speech recognition.
Okay, bigram too simple, so you need a more complex model.
Yeah.
Okay, Ken, hopefully that answered your question. If we have other questions, looks like Zuhair, I do see your comment in the chat. If you could use the Q&A button, that would be great. But I will ask your question here. Did you try fine-tuning conformer CTC model?
Do you mean like, yeah, if the question is that, can we fine tune these larger models? We did try doing that, but we did get better results by training our own models from scratch. If you fine tune large language models, they still don't give you the kind of performance that's needed.
Okay, great. And here's a relevant question too to that. Mark Tucker asks, where can we go to learn about training our own ASR models and hosting them?
Sure. So there are a lot of tools out there. Like I talked about Cordy. There are other speech recognition toolkits as well. So as long as you have your own data, you can play around with them. So Cordy is a good resource. They have a lot of updates on that toolkit. It's been around for a while, but they do keep updating it. So yeah, you can go to Cordy's website and learn how to train the
How do
model.
we spell that, Nikhita? How do we spell that?
It's KALDI. So I did mention it here. Yeah, this is how we trained some of our models. But I
Okay.
would say that there are a lot of things involved in this, and especially with like how you architect the acoustic model. So there's like a lot of architectural changes you could make, play around with the training scripts to make it work better.
And do you have a ballpark? I mean, I think it's going to be related to the complexity, but what are the initial costs for such a specific model? Do you have like maybe there's an alpha range that people should be thinking about from a budget standpoint?
Yeah, I think that depends on the kind of model you're training and at what scale. It depends on the amount of the data you train with and the specific vocabulary. And there's like a lot of components involved there. But yeah, I think with our experience, we did learn that it's more involved than it looks, and like we can definitely talk offline and help you guys out, figure out your particular domain.
Right. We will be sharing not only the video, but we'll be sharing Nikhita's contact information as well, so you can follow up with her directly. More great questions, though, coming in here. Nikhita, what are your thoughts on fine-tuning a domain general model for a specific domain with a reduced data? So maybe not a huge data set, but would you encourage people to be training models even with a small amount of data?
Yeah, I think that like we have played around with that, but even for a very general, like we had a customer survey chatbot, so that's more generic vocabulary. But we did find out that that did not give us very good results if we fine-tuned some of the open source models with our own data. Yeah, like I said, it's better to train from scratch using your own model, but it's not impossible.
Great. And let's see here. Beju says, what is the architecture that you use for training? How long did the training take you?
So for like a 75-hour model, it typically takes like under 8 hours on an A100 GPU. And what was the other question?
How long did the training take? I guess you asked that's what you said. The train took about, you said 8 hours?
Right. What was the other part of the question?
What is the architecture
Yeah,
that
so
you
we
use for
use
training?
we use a HMM neural network hybrid architecture. There are definitely other ways of doing it, but I think this gives the best results.
Great. Michael asks, how do you bootstrap a project with no domain-specific data to start with? Are there specific tools that you have or recommend for people that don't maybe have any of the source data that they would need to train a model?
Yeah, I think it depends on the domain. Again, if it's a very general model, then might be audio data already available. So you could use open source data sets. Or if you have a more specific domain, you could, if you have a system already, you could use paid solutions, get some data, transcribe it, or just record your own data and get it transcribed and, start
Right.
working with that.
Right. There were lots of data providers at the conference. I think LXT was one of the companies that priced themselves on as being a data resource. Um, when you, Kyle Rogers, you said, can you spell that? Are you referring to the Caldi platform? I think so.
No. For data, you can, you'll have to like record your own data if you don't have any, or you can resort to open source data sets.
Right. Yeah. Hugging Face, maybe. All
That's a good.
right. So let's see here. Where are we? Can you support non-English languages from Jordan?
Yeah,
I think
definitely.
you touched
Yeah,
on that with Spanish, right?
yeah. So as long as you have audio data for that, and like I mentioned, the dictionaries and the lexicon is usually available for most of the languages. So you can train with essentially any language as long as you have enough data.
Man, there's some just great questions coming in here. Mark asks, what improvements to ASR models are happening based on the new transformers versus the older machine learning approaches? But the thing I love about this question, I have to say, is, we started doing some machine learning events just in 2017. And it's just wild to think about that as old technology because it was so futuristic at the time. But here we are. Great question.
Yeah, I think you can always make use of new architectures as they come in. So if you set up this domain-specific model pipeline, you can always play around with newer architectures, and that's an advantage. So if you figure out the scope of your model and the vocabulary and everything, you can keep switching and updating with newer technologies.
And Kyle asks, how do you monitor post-production analysis and how do you retrain to retain the favorable goals?
Yeah, that's a good question. I think that, like I mentioned, you could do A/B tests. You can set up, pull data regularly from production. You can set it up based on how often you want to do it. But I would say like every 2 weeks, you could get data from production, get it transcribed, and then check the accuracy of your model on that. And that way you can recognize where the model is going wrong, or are people interacting with the system in unexpected ways. You can capture all of that and then retrain the model.
Well, also in where it's going right? You don't want to throw the baby out with the bathwater, right? So if the model is doing some things really well, you want to make sure you retain those things while you're training the rest of the model, right? So really interesting challenge.
Yeah, and just to follow up
Go
on
ahead.
that, you don't want to add a lot of general data to your model, because if you think you can improve the model by just keep adding more data, it can cause confusion in the model, and it can start going, it can start making mistakes that you did not anticipate.
Right, totally. CG asks, have you had the chance to try K2? Any perspective on such platform versus Caldi? And Kyle Rogers, Caldi is Kaldi.
Yeah, I think you could play around with any of these. I think Caldi is like one of the toolkits which has been available for a long time, and it's dependable. So we just work with that. But yeah, I mean, I think you can get the best results if you have good data. I think data is the bottleneck here, and not the pipeline that you use for training.
Okay, a few more questions here. How does this model differ from the NLU models made popular by Nuance's ASR technology?
Yeah, so like we did show you results from like Speechmatics and all these other available models. But I do think that for specialized domains, these models do not do that well. And we discussed about how high the word error rate can be, even when using, state-of-the-art models like Whisper.
Right, right. I think that's where a lot of discussion has been around NLU and LLMs. Um,
Yeah.
Mark Tucker asks, if you recommend Kaldi as an open source tool, what services or tools do you or your company provide? What is FreeClimb and how is it related to this topic?
Yeah, so Caldi, like it's just a toolkit. So it's been around for a while, but there's a lot of work involved in customizing the pipeline, the training pipeline. How do you even architect the neural networks? How many layers do you put in there? How often, how do you fine tune your models? And there are a lot of moving parts there. So we specialize in building domain specific models. And if you use Caldi off the bat, there are different ways to train. There are different training recipes. You don't get the same results with each pipeline. So we build custom pipelines, and FreeClimb provides this service to customers.
Thank you, Nikita. And Simon asks, have you considered building ASRs for non-written languages, for example, Cree or Navajo?
No, so yeah, I'm not familiar with those. But
Yeah,
yeah, I think ASR, yeah, you can work with any kind of symbols. Like if you can map the audio to some kind of symbol, even if it's not text, you can work with that and you can train models for those.
great. Yeah, that's a great question. It's interesting. Yes, I guess I wasn't aware that Navajo was unwritten. I do know that the Navajo Indians helped us win World War II with using their language as a way to yeah, well, I think you know the story. Anyway, looks like let me see. Oh, another question. It is not. Oh, yeah, it's not written so much anymore, right? But it was in the past. Yeah, I got it, Simon. Well, listen, this has been excellent questions. It looks like that is the end of the questions I think that we have not answered. And again, we will be following up with the video as well as Nikita's contact information. So we want to thank everybody. Let's big round of applause for Nikita Sharma, a data scientist with Veil FreeClimb. Nikita, thank you so much. Excellent presentation. I see the claps in the chat window. And again, folks, we will be getting this recording out to you. Thank you so much for joining us today, and hope everyone has a wonderful rest of their Thursday. Thank you, Nikita.
Thank you guys for joining.